Welcome back. In today's video lecture, we will look at the role of surface tension, in determining the work of cohesion, adhesion, and the spreading coefficient, right? So these things will be very important whenever we deal with application like lubricants, additives, right? Because the adhesion is going to be very crucial, in such application. Sometime when you are preparing the waterproof material, there you need to understand what is the spreading coefficient and things like that. Okay, because there we do not want the wetting property to be enhanced, right? So depending on the application, these aspects one has to look into in very detailed manner, right? So in today's lecture, we are going to look at these topics with somewhat more insight, right? Okay, so let us begin, right? Yeah. So as just now we mentioned, the work of cohesion, adhesion, and spreading coefficient, these parameters are going to be very crucial in coating applications, right? So we look at them in detail. Let's first start with the cohesion, okay? And we also have what is known as adhesion, okay? Whenever we talk about cohesion, one thing that we should understand is that it involves the interaction between the identical molecules, right? This is more of an interaction between the identical molecules, whereas this one is between dissimilar type, right? Interaction between dissimilar type, right? So in a nutshell, one can call cohesion as intramolecular. One can relate cohesion as intramolecular interaction, okay? Whereas adhesion as intermolecular. Right, I think this difference is very clear now. Right, so we talk about cohesion or work of cohesion. I denote work of cohesion as W subscript AA, which means that interaction between the like molecules, right? So, so we are going to follow a slightly different strategy. Let's say I want to understand the work of cohesion of a column of liquid, right? This is a column of liquid type A. Now, how do I understand this? I'm going to use a strategy, right? Using which I can calculate the work of cohesion. So what I can do is, what if I, break this or pull this column of liquid, okay? Pull this liquid column apart into two equal parts. Let's say if I, break them into two equal parts, let's say I have A and A, right? But whether you are breaking them into two equal parts or not, what is more important is the surface. So when you do so, you create two new energy surface, right? This is one energy, this is another energy, right? Or you can say you got two new surfaces, right? Now the question is, the work required to pull them apart is same as the work required to put them back, right? Okay, let's say if I know what is the work required to pull them apart, if I know that, it is easy for me to calculate or understand what is the energy or work required to put them back, right? Okay, it will be safe, correct? So in this way, I can, so using this strategy, I can calculate work of cohesion. So if I denote that as WAA, AA, stands for cohesion between identical molecules, right? So remember, now if I want to put them back, okay, whether they will combine to form, the column of liquid as they were originally. It depends on whether the process is spontaneous or not. Correct. So for that, we will have to associate this workup cohesion with what is known as delta G, okay, which is change in Gibbs free energy. In such case, we know that my final, the energy at final configuration minus energy at initial configuration should be negative. Only then this process of combining can happen, right, spontaneously. Otherwise, it is very difficult. One has to pay the energy penalty, right? So now we know this, that what is the energy at the final configuration? What is the energy at the initial configuration we spent? What is the energy we spent to arrive at the final? So these two things should be clear. Now, this configuration, that is final minus initial, now we know that this energy here is associated with the surface tension, right? So we have gamma A, gamma A here. Since energy is associated with the energy, since we have at the final configuration, this is my final configuration this is my initial configuration, right? Right. Initially, I started from this configuration. This is my final configuration. So what is my final configuration is, so it should be, 2 gamma, right? So I have got gamma A plus gamma B minus initial configuration is 0, because remember, there is no interface here, right? There is no interface here. So when you put them back, it is completely homogeneous. There is no new surface in this. There is no interface there. No interface exists in this case. So you will not have any energy at the when you talk about initial configuration. So in this case, it should be A, right? Because both are identical molecules. In this case, it will be simply gamma A itself. Okay. So this is nothing but work of cohesion. Now, similar way, let's say we have a column of liquid where I have got two type of molecule, which is A and B. Now, if you want to understand the work of adhesion in this case, what if I pull them apart into two? So, which means that I will have A and I will have B separately, right? Right. Now, if I use this similar strategy, gamma AB, subscript AB represent interaction between molecule A and molecule B. So which is supposed to be, so I have to associate this with the delta G, which is again final minus initial. Alright. Okay, so this has to be negative. So my final configuration is going to be gamma A plus gamma B. Okay, my initial, remember, here interface do exist, right? In this configuration, you have boundary A and boundary B. In between, you have got interface, right? So that you have to take into account, right? In the previous case, there was no interface, so you don't have any interface over this. So the energy at the initial configuration we have taken as 0, but in this case, it do exist. I mean, the interface do exist, so you have to take that into account. So this here, the interface, the energy at this point is nothing but gamma AB, right? So this is going to be my, the work of adhesion. So similar strategy, you can also use, let's say you have a solid surface and liquid. In this case, you have used this approach for a liquid column where you got A molecule and B molecule. What if I have to do the same exercise where I am spreading liquid on surface solid? Now, what is going to be my adhesion, right, in this case? So you have got A and B here too. Now, can we understand what is the work of addition? Can we write a work of addition for this case? Yes, you can write. So this you will have to write in this way, right? So because we have got liquid, right, which is in this case gamma A is going to be my L liquid, right? So it should be Lg. I'm going to write explicitly because this is associated with the surrounding, that is gas, right? So Lg and the gamma B has to be this one. So this is supposed to be Sg because this is associated with the surrounding. So it has to be gamma Sg minus gamma AB in this case will be, gamma SL, right? In this case it will be gamma SL. So you can write this also as, if I remember, if I have to use if I borrow from Young to Prey equation, I know what is this things, right? Gamma Sg minus gamma SL explicitly. So in that case, gamma Lg, I can replace this as gamma Lg cos theta, okay? So one would know that one would get work of addition for this case as gamma Lg into 1 plus cos theta. Okay, so this is very compact equation borrowing from Young to Prey, right? Right. So let's look at now spreading coefficient, okay? So well, spreading coefficient is just like a quick guideline. So by knowing the number, one can quickly say whether liquid, right, will spread nicely on the solid surface, given solid surface or not, okay? To say that, what you would do is, what people generally followed is, the same approach that we have used just now, delta G approach. But instead of delta G approach, what the convention that people followed was minus delta G, so that more positive favors the wetting and less positive doesn't favor the wetting. Okay, so which means that if spreading coefficient is negative, it will de-wet, whereas spreading coefficient, if it is very high positive, then it will wet, right? Spontaneously it will wet. So that is the idea. So for that, we have to use minus delta G approach, which means that you have to reverse this the approach that we have used just now. So it should be in that case initial minus final, right? Because you want it to be more positive, right? So that is the idea. So if I use this approach, let's say this is going to be my scenario where you have a surface, okay, and you have a liquid droplet. If I place this droplet on the solid surface, whether it will wet or not, right? So remember, we are considering the complete wetting, right? This is very important to understand. We are taking the case of complete wetting. So unlike the partial wetting that we have seen so far, in complete wetting case, you don't have theta, right? Theta doesn't exist. Conduct angle doesn't exist. So that is the condition we are using here. So in this case, what is going to be my spreading coefficient, which is spreading coefficient? Let's say if I call this as A and this one as B, what is the spreading coefficient of liquid A, spreading on surface B, right? In this case, initial minus final. My initial configuration says that it is simply gamma Sg because this surface associated with the surrounding, right? And minus my final configuration says that it is supposed to be gamma SL, plus gamma Lg, right? So you can also say this as gamma Sg minus gamma SL minus gamma Lg. So this factor, you can, by borrowing from Young to Prey, you can also say that it is simply nothing but gamma Lg as cos theta minus 1, right? Okay, so in this way also you can say, remember, you can also rewrite this spreading coefficient as WAB minus WAA, because we know WAB, which is nothing but gamma LG into cos theta plus 1, okay. If I write minus, let's say, 2 gamma LG, in this way, I will get equation, same as the spreading equation, right? Gamma LG cos theta minus gamma LG. If I compare this is going to be the same, right? If you compare this equation and this equation, both are same. So it is also, you can also say that spreading coefficient is same as the work of adhesion, right? WAB minus work of cohesion, right? So this is the relation that we have. So spreading coefficient in terms of work of adhesion and work of cohesion also one can define. So we have seen so far the cohesion, adhesion and spreading coefficient. Now we will look at the some example tutorial based on these concepts. Okay, right. All right. So let's look at the a problem, right? So this problem nicely describes the spreading coefficient concept, right? So you can see that in this problem, so the work of adhesion data has been found out by these authors, right? So here it involves carbon block. So here one of the component is carbon block. The other is these organic liquid. Okay, right. So use this data together with the surface tensions of the pure liquids. Okay, the surface tension of these liquids are not given in this problem, but we can supply that, right, as we saw, right, to calculate the spreading coefficients for the various liquids on carbon black, right, carbon black. So this is the kind of nanoparticle they use. So in this problem, they want us to interpret and justify the observation, which means that what is observation? So they say that when they mix equal quantity of water and organic liquid, which means that one phase is water and the other phase is different organic liquid in a different set of experiments, they observed that after some time, they observed that after shaking the mixture, they observed that the carbon particle, right, the carbon particle went exclusively to the organic liquid phase. What does it mean is, if we know the spreading coefficient, okay, if spreading coefficient is more positive, which means that this carbon with respect to a given organic liquid, if the spreading coefficient between carbon and this organic liquid is more positive, then it will prefer a particular phase only, organic phase only, right? So that is the observation. So they are asking us to justify this observation, which means that this carbon carbon black went exclusively into the organic phase, which means they don't want wet. They don't want to be associated with the water phase. That's why this carbon particle went into the organic phase. So we have to first calculate what is the spreading coefficient in these cases for different cases. Then if the value is so positive, so high, then we can say that yes, this observation is correct, otherwise the observation is invalid, right? So we will look at that now. So we have got this problem. I hope this Excel sheet is very clear to you. Yeah, so for different organic liquid, we have benzene, okay, toluene, carbon tetrachloride, carbon disulfide, ethyl ether, water. This work of adhesion has been reported by the authors. And this is the value I supply to you. This is taken from the textbook for, surface tension of liquids for these liquids. Now we know the spreading coefficient is simply nothing but work of adhesion minus work of cohesion, right? So work of cohesion is nothing but 2 into gamma Lg. So gamma Lg value we have reported here. So we just have to simply subtract gamma AB minus 2 gamma Lg. So in that way, you can say that, so these things is very clear. So we will just simply, minus, right? 2 times this one, correct? Yeah. So then we will get the spreading coefficient in this case. So we have got this as, okay, so if I simply Control C, you can see that the values are changing here. Look at the value for the water case. Look at this one, right? This is negative. In the case of spreading coefficient for water with the carbon black, the spreading coefficient is negative. That's why carbon particle doesn't want to stay in the water phase. They went exclusively to the organic phase. So in the rest of the case, spreading coefficient is highly positive. So it is encouraging that, it is justified that the observation made by the authors is correct. So one can say that it is because of the high spreading coefficient. That's why the carbon particle went exclusively to the organic phase. Okay. So I think this is clear now. We will stop here. We can continue from the next lecture. Thank you.